The last force topic that I'm going to go into is the cases where the force acting on a body is a function of some other variables. So force functions, what I'm talking about is these forces are functions of something else, time, position, etc. And so I'm going to talk about 3 cases here. And one of these is going to be relevant to medical stuff, biomedical engineering type things. So here are the 3 cases that we're going to talk about. The first one I'm going to talk about is time-dependent forces. So when the force that's acting on a body is a function of time. And we're going to see how you can use that to calculate position as a function of time and stuff like that. The second one I'm going to talk about is springs. And at first, we're going to, as this class goes on, we're going to keep having problems that we do and lessons that are related to springs. And at first thought, you might think, like, springs, the thing in my, grandmother's drawer in her kitchen, like, why is that worth spending so much time on? And the answer is that a lot of materials behave the same way that springs do. Almost all engineering materials within a certain range of loading behave like very stiff springs. And a lot of important calculations are done treating things like springs. Also, a lot of things in the body, when you're doing biomechanics, you treat like springs. Tendons act like springs in some ways. Bones act like springs over a very limited range of deformation. And so the list of applications kind of goes on, and that's why we have to introduce it here. And when I'm talking about springs, I want to mention that these are position dependent. So instead of the independent variable when we're talking about springs being time, the independent variable is going to be position. And then the last one, which is a medical application, is muscle models. It's often in many kinds of research projects and medical analyses, it's useful to be able to figure out how much force a muscle would apply in a given setting when the body's doing this. And, it's useful in sports science. It's useful in sometimes pre-surgical decisions for people who have, say, walking abnormalities. You do these analyses to try to figure out what the muscle is capable of doing, why isn't it doing what it's supposed to, and this kind of modeling can be useful in that case. And I can't talk about all muscle models. I'm going to talk about one that's very practical, very practically useful in human applications. And that is known as the Stanford model. Okay, so those are the things I'm going to talk about here. So first, I'm going to talk about dealing with forces when they're given as functions of time. And there are 2 things that you need to remember as we do this. These are both going to be really important. So the first one is since we're going to be using derivatives and integrals, if you're ever taking derivatives or integrals of trigonometric functions, cosine or sine, you have to switch your calculator over to radians. All of the angles need to be given in radians for this to work. And so we'll see some examples here where we're going to have our angles in radians. And the second thing we're going to see is that sometimes these functions are going to give us negative values. So if a force function gives a negative value, the meaning of that is you can think of it as a positive force in the opposite direction. Okay, so for example, for this second one, if you have an object that has a force going this way of negative 50 newtons, that's equivalent to this same object having a force in the opposite direction with a magnitude of 50 newtons. So that's what negative force values are always going to mean. It's just going to mean that the direction is switched. And if you know a force F of t, so we're assuming that that force is known as a function of time, you can use Newton's second law to calculate the acceleration as a function of time. And then you can integrate to find the velocity as a function of time, and then integrate one more time to get the position as a function of time. Remember that each one of these steps, since we'll be integrating, needs initial conditions to calculate those constants of integration. So for this, I'm just going to go straight into an example problem. I think that's the clearest way here to show how this works. So let's say that we have an incline of 20 degrees. And we have a mass of 0.1 kilograms. And there's a force applied in this direction. And that force is determined by the function t squared. Okay. And we want to know if this starts from rest at position 0, what's the function position as a function of time? Okay, so that's what we want to figure out, is position as a function of time. Well, we're going to use Newton's second law, which means we have to start with a free body diagram. I'm going to have my positive direction this way, up the ramp. And my free body diagram looks like this. We have a weight force acting down that's equal to 0.1 times 9.8. So this is 0.98 newtons down. And we are going to break this up into the two components. So I'm going to draw out this right triangle. This angle is 20 degrees. Then we have the pushing force from the ramp, perpendicular to the surface toward the body, and I'll call that N. And then we have the force vector T squared. You can see that this weight force is more than 90 degrees from our positive direction. Our positive direction is this way. And so the component, the leg of the right triangle that is parallel to the surface, we know that that force is going to have a negative value. And so now we'll go to Newton's second law and plug in all these forces that are parallel to the surface. We have negative 0.98 times the sine of 20. That's from SOHCAHTOA. The force T squared is in the positive direction. And all that is equal to the mass times the acceleration. If you multiply out this sine of 20 term, you get negative 0.921 plus t squared is equal to 0.1a. Now you can multiply both sides by 10, and you have your acceleration function. That's equal to 10t squared minus 9.21. What we really want is the position as a function of time, but we know that if we have the acceleration as a function of time, we can get the velocity by integrating with respect to time. So the velocity is equal to the integral of 10t squared minus 9.21 dt. And that is 3.3 repeating t cubed minus 9.21 t plus c. Okay, well, we have to figure out what this c is, and we're given that at time equals 0, this cart is at rest. So the velocity is equal to 0 when time is equal to 0. So our initial condition says that the velocity is 0 when time is equal to 0. So the first term goes away at time equals 0. The second term goes away, and you get that c is equal to 0. So our final answer for the function velocity as a function of time is 3.3 repeating t cubed minus 9.21 t plus 0. So I'll just leave it like that. And now to get position as a function of time, we can integrate again. So position as a function of time is the integral of 3.3 repeating t cubed minus 9.21 t dt. And that gives 0.83 repeating t to the fourth minus 4.61 t squared plus a new c. And now I'm going to use our initial condition for the position. We're given that when time is equal to 0, the position is 0. And so 0 is equal to 0 minus 0 plus c. And so our final value for the position as a function of time is 0.83 repeating times t to the fourth minus 4.61 t squared. And the c is 0. So this is our final answer for the position as a function of time. The next topic we're going to go into is springs. And we're going to talk about this a few more times in this class and then in the next class, 1202. And I want you to remember the same thing or one of the same things that I said to remember at the beginning of talking about forces as a function of time. I said that if a force value is negative, the meaning of that is that you treat the force as positive and switch the direction. And so that negative doesn't mean something fundamental about the nature of the force. It just means that the direction switches. Okay, so with forces, we're always going to think of the x equals 0 location as representing, so this is always going to be the position of the object when the spring is at its resting length. And the meaning of that is that the force applied to the object by the spring is 0. Okay, that's the significance of this. The force applied to the object by the spring is 0. Then, if you think of x this way, you can think of any x value that is positive, means that the spring is being deformed, or the object is deforming the spring by moving in the positive direction, whatever you've chosen as the positive direction. And x being negative means the object is deforming the spring by moving in the negative direction. And it doesn't matter which you're calling negative or positive. You always just, that's just always what the meaning is. So if you have this meaning for x, then the force applied by the spring to the object by the spring is negative kx, where k is the spring stiffness, or people sometimes call it the spring constant. It's the one constant you need to define a spring. Okay, so let's see how these signs work out, how the directions of these forces work out. So I'm going to just do a couple of sort of intuitive examples. I'm going to use a spring constant of 100 newtons per meter. And let's say that first we're going to, okay, and I'm going to choose my positive direction to be this way like I usually do. And let's say that you have a spring attached to the wall. The original position of the cart is here. Okay. And let's say that you move the object in the negative direction. So the black here represents the object's position after you've deformed it. Okay. Since the object is moved in the negative direction from its resting length, its position is negative, and let's give it a value. Let's say it's 2 centimeters. So x here is negative 0.02 meters, 2 centimeters. Okay, well, what does that tell us about the force that's applied here? And I guess before we do that, let's think physically about what would happen. Which way would this spring be applying a force to this body if we pulled it to the left? Okay, if we pull this spring to the left, the spring always applies a force to try to get itself back to its resting position. So that spring force we'd expect to be to the right. Okay, now let's see how the math works. So if we draw this body, the spring force, we're going to draw an arrow in the positive direction and multiply this arrow by the number negative kx. Well, negative kx is negative 100 times negative 0.02, because we've moved the object in the negative direction. And we get the double negative, and so this comes out to be positive 2 newtons. So we have a positive 2 Newton force pointing to the right, which is just what we expected intuitively. Okay, now let's think about the same thing, but this time we're going to push the cart to the right. Okay, so here's the starting position when the spring is not applying a force. And this time we push the cart to the right. So the coil bunches up like that. Okay, so this time we've moved the cart in the positive direction. And let's say x is equal to, in this case, positive 0.02. Okay. Well, what force do we expect this spring to, what direction do we expect this force to be that the spring's applying? The spring's always trying to push back to its resting length. And so we would expect this spring to push this cart back to the left. Okay? So we expect this spring to push in the negative direction. How does that work with the math? Well, there's the object. We always draw our force direction in our positive direction. It doesn't matter where the spring is. It doesn't matter which direction our positive is. We always just draw the arrow in the positive direction and associate it with a value of negative k times x. So we have negative 100, this time times positive 0.02 meters. And so that comes out to be negative 2 newtons. Well, what does it mean if we have a force vector to the right with a value of negative 2 newtons? It means that we can think of that as a force in the opposite direction with a value of positive 2 newtons. And so you can see that if you're thinking about the signs of these forces correctly, it always accounts for the fact that the spring is trying to get back to its resting position. Before we can do spring problems, the one additional thing that we have to talk about is what that spring constant means and how do you calculate it. How do you calculate it? Like, say that you open grandma's kitchen drawer and there's some springs there and you want to do some calculations and experiments or whatever. But first you have to figure out what the K value is, and it doesn't say it on the spring or anything. So how would you do that? So the spring stiffness meaning. Well, what you do to find the spring stiffness is apply a force F to one end of the spring. You can think of attaching the other end to a wall or something, or attaching it to the ceiling and hanging a known weight from it. And then measure how much the spring stretches due to applying this force to it or this weight to it. So we're going to measure the deformation delta L. That's not the length of the spring after the deformation. That's how much the length has changed. Then the spring stiffness is just equal to the force divided by the change in length. So in this example here, I said that the spring stiffness was 100 newtons per meter. That says that if I applied 100 Newton force to this spring, its length would change a meter. A meter is a lot. Most springs, unless they're very, very long, you can't stretch it a meter without damaging it. But this also could say if you apply 10 newtons to it, it stretches 10 centimeters, 0.1 meters. So, and that would give you the same value. Okay, let's do a spring example. So first, let's say that we don't, before this calculation starts, we don't know what the spring constant is. So for the first step, let's say we hang a 1 kilogram mass from the spring. And its length increases 4 centimeters. And so the first thing we're going to do is calculate that spring stiffness. What's the K value? Now, second, we're going to use this spring that now we know the spring constant for. And we're going to put it in a situation like this, where it's attached to a cart with a mass of 0.2 kilograms. I'm going to call my positive direction this way, although you could do this problem with your positive direction the other way and it would work fine. And let's say in this situation, we stretch the spring 5 centimeters, or you could think of moving the cart 5 centimeters to the right. So we're going to move the cart 0.05 meters to the right. and then we're going to release it. And the question is, exactly at the moment of release, what's the acceleration of the cart? Okay, so first we have to calculate the spring stiffness. I'm going to draw a free body diagram of the mass that we're hanging from the spring, and we said that that has the mass is 1 kilogram. And so we have a spring force like this, and the weight force, which is really the important thing, is 1 times 9.8, so that's 9.8 newtons down. We know that the change in length of the spring is 0.04 meters, and so the spring stiffness is 9.8 divided by 0.04 meters. This is newtons, this is meters, and so you get an answer of 245 newtons per meter. Okay, so, whoops, there we go. So now we're going to go on to the second part, and we're going to use this same spring but attached to a different object. But now we know what the spring stiffness is. And so I'm going to start with a free body diagram of this situation here. And like I said, it doesn't change anything about this problem that the spring is on the left now instead of the right. I'm still just going to do this free body diagram with my spring force going in whatever I chose as the positive direction. And I'm going to associate that with the value negative spring constant times the deformation. For part B, I said that we're going to move the cart 0.05 meters to the right. To the right means moving it in the positive direction. So this is going to be positive 0.05. And if you multiply that out, you get a value of negative 12.25. Then we have our two other forces. We have the weight force. That is 1.96 newtons. And then we have the normal force from the ground. And if you want to redraw this, you can redraw it. So now we know that we can treat this spring force as going the opposite direction with a magnitude of 12.25 newtons. And we have these two forces. And now Newton's second law says negative 12.25 is equal to the mass times the acceleration. And so the acceleration is in the negative direction with a magnitude of 61.25 meters per second squared. And so to visualize that direction, at the instant you let go of this object, it has an acceleration of 61.25 meters per second squared to the left. So as always, what we see is that the spring is trying to return itself to its resting length. That's what spring forces always do. They don't always succeed at returning it to its resting length, but that's always the direction of the force that they're applying. The last topic I want to go into today is muscle modeling. And this has a lot of medical and physical therapy and sports applications. The most well-known muscle model is called the Hill model, and it represents a single contractile element of a muscle. That's not super practical if you're trying to use this in medical situations. So I'm going to talk about kind of a broader model that instead of representing a single muscle fiber, it represents a whole muscle group or an entire muscle at once. And this model, people tend to refer to this as the Stanford model. And so, yeah, like I said, this is applicable to an entire muscle. So that's why I'm going to use this one. We have one strand that's actin and one myosin strand, and they are connected in a whole bunch of places by this connection between the actin and the myosin. So that's what the connection that I've shown there. And when a certain event takes place in the muscle fiber, action potentials tell the fiber to generate force. What happens is the actin, let me write this on here. So this is actin, this is myosin. The actin changes its shape and pulls the fiber. You can see that this actin fiber is moving to the right relative to the myosin. Okay, so that's what happens microscopically when a muscle fiber contracts. So this is called the active unit of a muscle. And this active contraction is initiated by action potentials in the muscle cells. And what that action potential does is cause a flood of ions to move across the cell membrane. And because of this large motion of ions across the cell membrane, you actually can detect an electrical signal when a muscle is activated. So because these charged ions move across the cell membrane, you can detect electrical signals when the muscle is activated. This practice of measuring the electrical signal to see when muscles are being activated is called electromyography. And since that's a really long word, people tend to just call it EMG. Not only can you detect that electrical signal, by the way, you can also cause muscles to contract by applying a voltage to these muscle cells. And that can be done on muscles even when an animal is not alive. You can do it with, frog muscle cells. You can get them to contract by just applying voltage across the cell membrane. Okay, so this Stanford model that we're going to talk about, the force applied, force generated by a muscle depends on four things. So the force generated by the muscle depends on four variables. The first one is just really just a measure of the size of the muscle. I'm going to call this the strength, but we can think of this as like a baseline force that muscle is capable of generating under certain conditions. And well, those certain conditions are that the muscle length is not changing as those muscles contract, that the muscle is being fully activated, so the muscle is fighting as hard as it can to contract, and that the muscle is at its resting length. So, okay, this first one is strength. The second one is the level of activation. And this is something that you can measure with EMG. So if somebody is doing some activities and you have EMG electrodes hooked up to a muscle, by the strength of the electrical signal that you're getting, you can tell how many muscle cells in that big muscle group are being activated to try to accomplish this task. And that's what that activation number is telling you. If the muscle is completely relaxed, activation is 0. If that muscle is tensed as hard as it can be, then the activation level is 1. The third is the length of the muscle. And muscles can be all sorts of different lengths, but what we really want here is the length of the muscle compared to its normal length, or it's the shortest it can be or the longest it can be. So this is like a normalized value that goes from 0 at its shortest to about 1.7 or 1.8 at its longest. And then the fourth one is the muscle velocity. So that's saying how quickly the muscle is lengthening or shortening. So this is like the speed of lengthening or shortening. And this is also normalized, so this value goes from -1 to 1. And the total force generated by the muscle is the strength of the muscle. That's the isometric force. That's just a value telling you how big or how strong the muscle is, times this sort of complicated thing, the activation value between 0 and 1, times a function representing the length of the muscle. It's a function of the muscle length. And I'm going to give you these functions after I write this down. times a function of the speed of contraction of the muscle or elongation of the muscle, and that's a function of the muscle velocity. And then we're going to add to that term a function of the passive resistance of the muscle. That is, you can't stretch a muscle with no resistance. The muscle fights against that. And that's not because of activation of the muscle. That's just because it takes a while for these actin and myosin connections to be separated and then reattach. And this is a function of the length. Okay, so let's go through all of these functions that are in this big function. So the first one is this FL, which is a function of L. And all of these that I'm giving you are really just kind of rough estimates. They're really just designed so you can see the relationships between these things, and they can tell you some useful things about how a muscle behaves in different conditions, but numerically they're not very accurate. Okay, so this function of the length is negative quantity normalized length of the muscle minus 1 squared plus 1. And I'll show you sort of what that looks like. So let me get a picture. Okay, so that's what that function looks like. So what that says is when the muscle is as short as it can possibly be, okay, that's over here at length equals 0 on the left side, you can see that the muscle cannot generate really any active force at that point. The largest active force the muscle can provide is when the muscle is in its kind of middle resting length, and that's at this value of 1. Okay, and so when the muscle is really short, and then also when the muscle is really long, it can't generate as much active force. That just has to do with how many of those myosin and actin connections are made at that length. Next, is the active contribution depending on the velocity of contraction or lengthening. And for this, I'm going to use the function 0.75 times the cosine of pi over 2 times the quantity v plus 1. And then we're going to add 0.75 to that. Here, this needs to be in radians. So when you're doing this calculation, you need to have your calculator in radians. Okay, so what does this sort of ugly function look like? So now I'm going to get my function fv versus v. And you can see that when the muscle is shortening, it produces a small active force. When the muscle is lengthening, it produces a big active force. And then finally, the function representing the passive resistance to stretching. So this is the passive force, and it only depends on the length of the muscle. And I'm going to approximate this as 0.25 times e to the power of the length, and then all that minus 0.25. And what that function looks like is basically there's no real passive resistance when the muscle is short, but as it gets longer, the muscle resists being stretched more and more. And so for the example problem, there's an example problem, a homework problem with a few parts in it, where it's going to ask you to input some values and calculate what the muscle forces are and compare these different conditions. What you have to do in that case is it's going to tell you a muscle length value, a muscle velocity value, an activation value, and it's going to tell you this isometric force, this muscle strength. You're going to plug those into these three functions and then multiply all these things out, and it's going to tell you the force that the muscle generates.